Far from the warm inner solar system, the space between the Sun and the nearest stars is not empty. It is a region shaped by the Sun's outward breath, a continuous flow of charged particles called the solar wind. This wind carries the Sun's magnetic field with it, spreading into space in a vast, expanding bubble. That bubble is known as the heliosphere. It surrounds the planets, extends far beyond the orbit of Neptune, and forms the broadest local environment that any small body must cross as it moves inward. In this outer realm, sunlight is weak and cold dominates. Surfaces stay dark and stable for long spans of time, and many materials that would quickly change closer to the Sun can remain unchanged for ages. At the most distant edges of the heliosphere, the solar wind meets the thin gas and dust of the interstellar medium, the material that fills the space between star systems. This outward pressure of the solar wind slows and bends there, and the Sun's influence becomes less direct. This boundary region is not a hard wall. It is a complex set of transitions where the solar wind gradually yields to surrounding space. Within it, energetic particles, magnetic fields, and sparse matter interact in ways that can vary over time as the Sun's activity rises and falls. Even so, the heliosphere still marks a practical boundary for how sunlight, magnetic conditions, and particle flows behave in the solar system at the largest scale. It is within this broad frame that the object designated 3I Atlas belongs in the story. Before it becomes a point on a telescope image, before it is traced as a path against background stars, it exists as part of a population of bodies moving through deep space. Some of those bodies are born with the solar system bound to the Sun by gravity and following long, slow orbits that reach far outward. Others pass through from outside, arriving with a speed and direction that reflect conditions beyond the Sun's domain. In both cases, the first part of the journey toward the inner planets takes place in the cold outer regions, where the main forces are gravity and the faint push of sunlight, and where the signals available to observers are weak and easily confused. In the outer solar system, the Sun's gravity still rules motion, but it acts across great distances with a gentle hand. A small body far from the Sun moves slowly, and its path can be altered by modest changes in speed and direction. The major planets add their own gravitational influence, not as constant pulls, but as moving sources of perturbation that can shift an orbit over time. Jupiter, Saturn, Uranus, and Neptune matter not only because of their mass, but because they can change the future track of an object through a close passage, even one that remains far in absolute terms. In this wide arena, the difference between a bound orbit and an unbound path can be subtle in early measurements, and it depends on precise tracking and careful reference frames. The sunlight that reaches these distances is weak, and that weakness shapes nearly everything that can be observed. A small body does not shine on its own. It is seen because it reflects sunlight, and if it becomes active because it scatters light from dust and emits light from gas molecules excited by solar radiation. Far out, the reflected sunlight is faint. If the object is small, dark, or distant, it becomes almost indistinguishable from the background of stars and galaxies. Wide-field survey telescopes search for such objects by scanning large areas of the sky, repeatedly looking for points of light that move slightly between exposures. This method depends on contrast. It also depends on time. The object must be detected in more than one image, so that its motion can be separated from noise and from the many fixed sources in the sky. The outer solar system is also the region where cold traps can preserve volatile materials. Volatiles are substances that change phase easily, often turning from solid to gas when warmed. Water ice is familiar, but many other ices exist, including carbon dioxide ice, carbon monoxide ice, methane ice, and ammonia-bearing compounds. Which volatiles remain stable at a given distance depends on temperature, surface properties, and how heat moves through the body. In deep cold, these substances can stay locked in place. As the object moves inward and sunlight strengthens, some volatiles can begin to sublimate, a process where a solid turns directly into gas. That gas can carry dust away with it, forming a diffuse envelope called a coma and sometimes a tail. Yet at very large distances, only the most volatile substances are expected to drive strong activity, and even then the activity can be weak, intermittent, or hidden beneath a surface layer that insulates deeper ice. This outer context matters for the phrase quietly defying expectations, because expectations in astronomy are often built from populations. Survey teams and dynamicists. The scientists who study motion under gravity have well-tested ideas about how comets and asteroids behave as they approach the sun. They know typical ranges of brightness, change typical patterns of activity, and typical uncertainties in early orbital solutions. They also know that rare objects can violate simple assumptions, not because physics fails, but because the object's properties and its history differ from the average case. In the outer solar system, even a small mismatch between an assumed reflectivity and the true surface reflectivity can lead to a large difference in estimated size. A small error in the measured position of a faint point of light can change the inferred orbit in meaningful ways. A weak outgassing jet can nudge motion slightly, producing a deviation that must be separated from normal gravitational effects and from measurement noise. None of these require unusual explanations. They require careful framing and a disciplined approach to what the data actually contain. The heliosphere adds another layer to that discipline. Charged particles and magnetic fields influence dust grains and plasma around active objects. The solar wind can shape the direction and structure of ion tails, which are made of charged gas, and it can affect how material spreads. It does not steer the nucleus itself in any meaningful way, but it affects what observers see when they image the surrounding cloud. Far from the sun, the solar wind is still present, but the details of its interaction with a weak coma can be hard to detect. If the coma is thin, the object may appear nearly stellar, with only a slight fuzziness that depends on the telescope, the atmosphere of Earth, if the observation is ground-based, and the processing pipeline used to detect moving sources. A body can be active yet appear quiet in early data because the signal is near the limit of detection. Beyond the heliosphere, the interstellar medium is thin, but it is not irrelevant. It sets the broader background through which any true interstellar visitor travels. It contains gas, mostly hydrogen and helium, and small dust grains. Over very long times, these grains can alter surfaces through tiny impacts and chemical processing. Cosmic rays, high-energy particles from distant astrophysical sources, can penetrate surface layers and drive slow changes in chemistry. Starlight from the Milky Way adds a faint background glow. These influences are subtle, but they matter, because they shape what an object looks like when it finally enters the domain of sunlight, strong enough to reveal it to surveys. A surface that has been processed for a long time can become darker, or it can develop an insulating crust that suppresses early activity. Another surface might remain relatively fresh if it was recently fractured, or if it experienced heating events in a different star system before arrival. The physics remains the same, but the outcomes vary. Within this widest region, the most important scientific habit is to separate environment from object. The environment is the heliosphere, its particle flows, its magnetic structure, and the background interstellar medium pressing against it. The object is a small body, whose path is set mainly by gravity and whose light is a faint mixture of reflected sunlight and any additional scattering from dust or emission from gas. At this stage, the story does not require details of rotation composition or internal structure. It requires only a clear understanding of what it means to notice a moving point of light in a vast, cold volume, and to begin measuring its motion in a space where the sun's influence is strong enough to guide it, but not strong enough to make it obvious. 3. I-Atlas moves within this frame as a member of a broader class of small bodies that pass through the outskirts of planetary systems. The outer solar system is not a quiet void. It is a working region of dynamics and faint physics where the simplest forces dominate and where observations begin at the edge of detectability. In that setting, expectations are not promises. They are averages built from many cases, and they can be bent by any object that arrives with unusual geometry, unusual surface properties, or simply a combination of distance, faintness, and timing that makes early measurements delicate. The outer frame holds steady regardless. The heliosphere remains the large, enveloping context, and within it, the first scientific task is to locate, measure, and describe using only what the sky offers at the largest scale. The first practical contact between a distant moving object and human knowledge is rarely a dramatic image. It is more often a string of measurements made under strict limits. A survey telescope points at a region of sky, takes an exposure, then returns to the same region later. The raw frames contain stars, faint galaxies, detector noise, and the imprint of Earth's atmosphere if the telescope is on the ground. A moving object appears as a point that shifts slightly between exposures. If the object is faint, it may not stand out in any single image. It can become visible only after the images are compared, aligned, and processed to remove fixed background sources. This early stage is where the designation 3I-Atlas takes shape, not yet as a physical description, but as a candidate with coordinates, timestamps, and brightness estimates. ATLAS is a survey system designed to find near-Earth objects by scanning large areas of the sky frequently. Its strength is cadence, the rhythm of repeated observations. Cadence makes motion visible. The survey's software searches for consistent patterns linking detections that belong to the same moving source, while rejecting those that match known stars, cosmic rays, satellite trails, or processing artifacts. When a candidate is found, it is reported with a measured position on the sky and an estimate of brightness. The position is usually given relative to a reference star catalog, and its precision depends on factors like image quality, atmospheric seeing tracking accuracy, and how well the object's light profile matches the assumptions of the detection algorithm. For a faint source, small systematic errors can matter. The sky position alone is not the orbit. It is a line of sight. To infer an orbit, observers need multiple positions over time. Each position pins down where the object appears against the star field at a known time. With enough points, a preliminary orbit can be fitted using the laws of gravity and the geometry of observation. This is a problem of inference. It contains uncertainty from the start, and that uncertainty shrinks as more data arrive. Early on, different orbits can fit the same short arc of motion. This is especially true when the object is far away, because parallax, the apparent shift due to Earth's motion, is small and hard to separate from the object's own motion. It is also true when the object's motion is nearly along the line of sight, because the change in sky position is then slow. In such cases, the first orbit solutions can be unstable not because the object is strange, but because the data are sparse. Once a preliminary orbit is computed, survey teams and central data services compare it against catalogs of known objects. If the candidate does not match any known asteroid or comet, it becomes a new discovery. Follow-up observations then become urgent, not in an emotional sense, but in a mathematical sense. Each additional data point strengthens the orbit fit and reduces the range of plausible futures. Other observatories are asked to observe it. Telescopes with larger apertures can measure fainter objects more precisely, and instruments with different filters can provide color information, a measure of how brightness changes with wavelength. When possible, multiple observatories at different locations contribute, giving a longer observational baseline and improved constraints. The conditions of discovery shape the earliest description of 3-eye atlas. The object's reported brightness depends on the filter used, the exposure time, and the calibration. Brightness at discovery is not a physical size. It is a measure of how much light reaches the detector. The same brightness could come from a small, bright body, a larger, dark body, or a body surrounded by dust that increases the scattering area. In the outer regions, activity can be weak, but even a thin coma can bias the brightness upward, making the nucleus appear larger than it is. Conversely, a dark surface can make a sizable nucleus appear small. Early reports therefore carry hidden assumptions. They often assume a typical reflectivity, also called albedo, to estimate size from brightness. Albedo is the fraction of incoming light reflected. Most small bodies are dark, but the range is wide. Without direct measurements, the size estimate remains a bound, not a fact. Color measurements add another constraint. Color here means the difference in brightness measured through different filters, not a visual hue as seen by the eye. A redder color can indicate certain surface materials or dust properties, while a more neutral color can suggest different mixtures. Yet color can also be affected by the presence of a coma, by phase angle, and by calibration differences between instruments. Phase angle is the angle between the sun, the object, and the observer. It changes how sunlight scatters off surfaces and dust. At some phase angles, an object can brighten more than expected, a phenomenon tied to the way rough surfaces and particulate layers scatter light. In early observations, phase angle effects can be substantial, and they can be mistaken for changes in activity if not handled carefully. The first weeks after discovery often involve a steady accumulation of astrometric data. Astrometry is the measurement of precise positions on the sky. Each astrometric point is a coordinate with an uncertainty. Fitting an orbit means finding the path through space that best matches all points within their uncertainties while obeying gravity. The standard approach begins with a gravity-only model using the Sun and planets as masses that pull on the object. If the residuals, the differences between observed positions and model predictions, show patterns larger than the expected errors, additional effects are considered. These can include subtle corrections for Earth's rotation relativistic effects near the Sun or non-gravitational forces due to outgassing if the object is active. Importantly, the consideration of additional effects comes after the basic fit, not before. In the early stage, the simplest model is tested first. This is also where the designation begins to matter. A 3I designation implies an interstellar object with the letter I indicating interstellar and the number indicating sequence in the category. The assignment of such a designation follows from a best fit orbit that appears unbound to the Sun, meaning the object's path is hyperbolic when expressed in the appropriate frame and after accounting for planetary perturbations. The key is the object's velocity relative to the Sun at large distance. If that speed remains above the escape speed, the object is not bound and therefore is not a long-term member of the solar system. Yet the determination depends on precise data and on careful handling of reference frames. Early in an observing campaign, the uncertainty on this classification can be non-trivial. An orbit can appear more hyperbolic than it truly is if the data arc is short or if systematic errors are present. It can also appear less hyperbolic if key data points are missing. The classification is therefore a measured conclusion, but it is also a conclusion that becomes firmer with time. Alongside orbit-fitting observers, look for signs of a comet-like coma. In survey images, a coma can appear as a slight broadening of the object's light profile compared to nearby stars. It can also appear as a faint asymmetry, a hint of a tail. But at the detection limit, these clues can be ambiguous. Atmospheric blurring can broaden star images, guiding errors can elongate them, and image subtraction can introduce artifacts. Therefore, early coma claims tend to be cautious. Higher resolution imaging can help, as can stacking multiple exposures to improve the signal. If a coma is confirmed, it supports the presence of volatiles and ongoing sublimation. If no coma is seen, it does not rule activity out. It only bounds it at the level the observations can detect. In this discovery and survey region, the phrase quietly defying expectations can arise from the tension between typical patterns and the specific details of the data. A small object might brighten more slowly than a typical comet at the same distance. It might show a subtle deviation in its sky track that is larger than expected from a gravity-only model, yet still within the realm of natural outgassing. It might show colors that do not match the most common solar system populations. Or it might simply appear and persist as a faint, steady point whose orbit solution remains unusually sensitive to small updates, not because the object is capricious, but because the geometry of observation and the limits of measurement make the inference delicate. The scientific focus here remains on observation conditions and the pipeline from photons to positions. 3I Atlas becomes knowable through a chain of carefully constrained steps: detection, linking, reporting, follow-up, orbit fitting, and classification checks. Each step carries uncertainty. Each step can produce apparent surprises if the object sits near the boundary, where usual assumptions fail. In this section's region, the most faithful description is patient and procedural. The object is not yet a fully described body. It is a moving source in survey data becoming more real as more measurements narrow the range of what it can be. Once 3I Atlas is detected repeatedly, its path across the sky becomes a disciplined sequence rather than a single event. Each observation is a time-stamped coordinate. Together, those coordinates define a track and apparent motion relative to background stars. The first scientific task in this region is to translate that apparent motion into a physical motion in space. This translation is not direct. It requires geometry because every observation is made from a moving platform. Earth rotates, Earth orbits the Sun, and the observatory itself sits at a particular latitude and altitude. Even a space-based observatory moves. The result is that the same object will appear in slightly different places depending on where and when it is observed. This effect, called parallax, is small for distant objects, but it is still present, and it is essential for determining distance and orbit. An early orbit solution is built from a short arc, a limited slice of the object's full path. In that short arc, the object's motion may look close to linear on the sky. A line can fit many different three-dimensional trajectories when distance is not well known. As additional observations extend, the arc curvature becomes measurable. Curvature in this context is not a curve drawn on a screen. It is the subtle change in direction and speed of the object's apparent track as gravity and observing geometry act together. When curvature becomes clear, the orbit fit strengthens and uncertainties shrink. This is why follow-up is so important. A longer arc separates competing models that were indistinguishable before. The orbit is usually expressed in terms of orbital elements, a set of parameters that describe the size, shape, and orientation of a trajectory around the Sun. For an unbound object, the mathematics still uses a conic section, but the shape is hyperbolic rather than elliptical. The elements include the closest approach distance to the Sun, called perihelion distance, the orientation of the orbit relative to Earth's orbital plane, and the time of perihelion passage. Another parameter is eccentricity, which describes how stretched the orbit is. For bound orbits, eccentricity is less than 1. For a perfect parabola, it is equal to 1. For an unbound hyperbola, it is greater than 1. The classification of interstellar depends heavily on whether the best fit eccentricity exceeds 1 by more than the uncertainty when expressed in an appropriate reference frame and after accounting for gravitational influences of the planets. Reference frames matter because the solar system is not a fixed stage. The Sun moves relative to nearby stars, and the planets move relative to the Sun. When an orbit is first computed, it is often described in a heliocentric frame centered on the Sun. But for determining whether an object is truly interstellar, astronomers often consider the object's velocity relative to the solar system barycenter, the center of mass of the solar system, which is slightly offset from the Sun because of the planets, especially Jupiter. This barycentric view reduces certain short-term effects from planetary motion and gives a clearer sense of the object's incoming and outgoing speed at large distances. Small differences between heliocentric and barycentric solutions can matter when the object's excess speed is modest. A confident classification requires that even under barycentric analysis and within uncertainties, the object remains unbound. The process of orbit fitting produces residuals, the differences between observed positions and predicted positions. Residuals are not just errors, they can contain information. If residuals are random and consistent with measurement uncertainties, the model is adequate. If residuals show a pattern, something is missing. The missing piece could be a systematic bias in the data, such as a slight timing offset or a catalog error. It could be an unmodeled gravitational influence, such as an underestimated planetary perturbation in a close approach. Or it could be a non-gravitational acceleration acting on the object itself. At this stage of the story, the emphasis remains on the orbit fit, not on an assumed cause. The scientific practice is to test whether the pattern persists across different datasets and observatories, and whether it survives careful data cleaning. The phrase quietly defying expectations can attach to orbit behavior in several grounded ways. One is sensitivity. For some objects, adding a small number of new measurements can shift the best fit orbit more than is typical. This can happen if the observational arc is still short relative to the distance and speed, or if the object's motion is aligned in a geometry that hides key parameters. Another is a consistent pattern of residuals that cannot be removed by ordinary corrections. If the residuals suggest that the object is slightly ahead or behind, where gravity-only motion would place it, and if the pattern grows with time, it points to a small acceleration along the trajectory. Such accelerations have natural explanations in active small bodies. Outgassing, the release of gas from sublimating ice, can act like a gentle thruster. Even weak outgassing can produce measurable effects over weeks or months, especially for small objects with low mass. However, confirming non-gravitational acceleration is challenging. The data must be good enough to distinguish it from noise. The acceleration must be consistent across independent observations, and the model used to represent it must be appropriate. In comet orbit work, non-gravitational acceleration is often represented by parameters that scale with distance from the Sun, reflecting the idea that sublimation increases as sunlight strengthens. The exact scaling depends on which volatiles are active and on the thermal properties of the surface. Water-ice sublimation dominates closer to the Sun, while carbon monoxide or carbon dioxide can dominate farther out. If 3I Atlas shows any hint of non-gravitational effects at large distances, the natural explanation would tend toward these more volatile substances, or toward localized jets from small patches where ice is exposed. Yet even then, the effect on brightness might be small, and the coma might remain difficult to detect. Another orbit-related expectation involves approach direction. Interstellar objects do not arrive from random directions in the sky in a simple sense, because the Sun moves through the local interstellar medium, and that motion creates a preferred incoming direction for certain small particles. For larger bodies, the arrival directions reflect the distribution of ejection processes in other star systems and the dynamics of galactic motion. In practice, each new interstellar candidate is checked against known populations and against the statistical distribution of possible incoming velocities. Astronomers estimate the object's inbound direction, its radiant and its velocity at infinity, meaning its speed relative to the Sun when far away before the Sun's gravity accelerates it. If that inbound velocity is unusually high or unusually low compared with expectations, it can prompt closer scrutiny. But unusual does not mean impossible. The distribution of velocities has tails, and the small number of known interstellar objects means the observed sample is limited. A single object can appear atypical simply because the sample is small. The orbit also interacts with the planets. If 3I Atlas passes near a major planet, the planet can alter its path through a gravitational assist-like effect, changing the outgoing direction and speed relative to the Sun. This is a normal gravitational interaction. Even a passage that is not extremely close can produce a measurable deflection. When orbit predictions include such encounters, the uncertainty can increase temporarily because a small change in the incoming track can produce a larger change in the post-encounter track. If an encounter is anticipated, astronomers refine the orbit to predict closest approach distance and timing. They also consider the possibility of observational opportunities, because a closer distance can make the object brighter and easier to study. Yet in this region of the story, the focus remains on the geometry of the orbit and the mechanics of prediction, not on future outcomes. For 3I Atlas, the quiet aspect can also arise from steadiness. A typical comet from the solar system might show increasing activity as it approaches the Sun with a noticeable change in brightness that follows a rough power law with distance. If 3I Atlas brightens more slowly, or if its brightness varies in a way that suggests rotation without strong activity, it can look less like a typical comet, even if it is a natural icy body. That mismatch between expected brightening behavior and observed light can feed back into orbit work, because if brightness changes are driven by a coma, the measured centroid position can shift slightly depending on asymmetry in the coma. This is a subtle effect, but for high-precision astrometry, it matters. If the coma is lopsided, the measured center of light may not match the nucleus location. This can create systematic astrometric offsets that mimic acceleration. Therefore, careful orbit work often includes checks for coma morphology and for differences between measurements taken in different filters or with different image scales. In this third region, the story remains at the level of motion inferred from sky tracks. 3I Atlas becomes a trajectory rather than a dot, and the trajectory is refined through repeated measurement and careful modeling. Defying expectations in the scientific sense can be as small as an orbit that remains more uncertain than typical for the amount of data collected, or as small as residuals that persist when they should wash out. It can also be as simple as a hyperbolic solution that becomes stronger and more stable with each new night of observations, confirming an unbound path with increasing confidence. Whatever the outcome, the discipline is the same. The orbit is not a narrative device. It is a measured geometry, tested against data improved with time and kept honest by uncertainty estimates that shrink only when the sky provides enough information. The motion of 3I Atlas is first seen as a shift on a detector, but the deeper description of its approach requires a careful look at geometry. Geometry here means how the object, the Sun, Earth, and the planets are arranged in space over time, and how that arrangement shapes what is measured. An object can appear to move quickly across the sky, not only because it is fast, but also because it is close. It can appear slow because it is distant, or because its motion is aligned toward or away from the observer. Therefore, when speed is discussed, it must be anchored to a defined quantity. Astronomers separate apparent angular speed on the sky from physical speed through space, and they distinguish speed relative to Earth from speed relative to the Sun and the solar system barycenter. In celestial mechanics, the cleanest description of an incoming object begins with its velocity far from the Sun. As the object approaches, the Sun's gravity accelerates it. This acceleration is predictable. It depends on distance and follows an inverse square law. The closer the object gets, the stronger the pull and the higher the speed, even if the object begins with a modest inbound velocity. For a bound object that starts near rest at great distance, the approach can still become swift near the inner solar system simply because of gravitational fall. For an interstellar object, which already has an inbound speed relative to the Sun, the approach speed can be higher still. The key difference is not the speed near the Sun alone. It is whether the object's total energy relative to the Sun is positive, meaning it can leave and not return, or negative, meaning it remains bound. Approach geometry includes the direction from which the object enters the solar system. This direction can be expressed in celestial coordinates, and it can be related to the plane of the ecliptic, the plane of Earth's orbit. Some objects approach near the ecliptic plane, while others arrive on steeply inclined paths, crossing the plane at sharp angles. Inclination affects encounter probabilities with planets and also affects observation conditions. A high-inclination object can move through regions of sky where survey coverage is less dense, depending on how surveys prioritize the ecliptic, where most asteroids reside. A low-inclination object can blend into a sky region crowded with known minor planets, increasing the complexity of linking detections. Thus, even before physical interpretation, geometry shapes how quickly an object is recognized and how robustly it is tracked. The phrase "quietly defying expectations" can be grounded here in the way 3I atlases approach geometry interacts with speed estimates. Early orbit solutions can suggest unusually high inbound velocity, unusually low inbound velocity, or a direction that is uncommon among known small body populations. Each of these can be real or can be an artifact of uncertainty. When the observing arc is short, distance is uncertain. Distance uncertainty feeds directly into velocity uncertainty. A small change in inferred distance can produce a meaningful change in inferred speed because the object's three-dimensional position and motion are reconstructed from line-of-sight measurements. As more observations accumulate, the geometry becomes constrained and the speed estimate stabilizes. There is also the geometry of observation itself, which includes the position of Earth relative to the Sun and the object at the time of observation. When Earth and the object are on opposite sides of the Sun, the object can be near conjunction and hard to observe because it lies close to the Sun in the sky. When Earth is positioned such that the object appears far from the Sun on the sky, it is easier to observe and more data are gathered. The elongation angle, the apparent separation from the Sun, matters strongly. Surveys avoid pointing too close to the Sun because of bright sky and instrument safety. Therefore, an object's detectability depends on whether its approach geometry places it in accessible sky regions during the critical early weeks. Approach geometry also determines phase angle, the Sun object observer angle. phase angle influences brightness because it changes how much of the illuminated side is visible and how light scatters. At small phase angles, an object can appear brighter due to opposition effects, where shadows on a rough surface are minimized, and coherent backscattering can increase brightness. At large phase angles, brightness can drop, and the object can be harder to detect. For dusty coma, scattering properties can make brightness behave differently from a bare surface. Therefore, the same physical object can look brighter or dimmer depending on viewing geometry. If 3I Atlas appears to brighten or fade in a way that does not match simple distance-based expectations, geometry is the first place to look before invoking changes in activity. The approach geometry relative to planets matters too. A path that passes near Jupiter or another giant planet can be altered. Even without a close encounter, the planet's gravity can shift the orbit slightly. More importantly, the prediction of such an encounter requires precision. If the predicted closest approach distance is uncertain, the predicted deflection is uncertain, and the future path becomes harder to forecast. This is not a failure of physics. It is a consequence of sensitivity in gravitational dynamics when trajectories pass through regions where small differences matter. In this region, the scientific task is to constrain the approach path well enough that predicted planetary perturbations can be quantified. The language of incoming can also mislead if it is not carefully defined. An object can be incoming relative to Earth, meaning its distance to Earth is decreasing, while its distance to the Sun might be increasing or decreasing depending on where it is in its orbit. For a true inbound interstellar object, the distance to the Sun is decreasing as it approaches perihelion at least over the relevant time interval. Yet in the sky, the object's apparent motion can slow or even reverse temporarily, due to Earth's own orbital motion, producing a retrograde loop in apparent coordinates. This apparent reversal is common in solar system observations and does not reflect the object turning around. It is a perspective effect. Therefore, the most stable description uses heliocentric or barycentric quantities rather than sky plane impressions alone. If 3I Atlas is reported as quietly defying expectations in its approach, one grounded reason could be that its inbound speed relative to the Sun is measured as modest, perhaps close to the threshold where classification is sensitive. In that case, the object's hyperbolic nature might be real, but not extreme, and careful barycentric analysis is required. Another reason could be that the object's incoming direction is such that it passes through sky regions with limited follow-up, making the orbit refinement slower than normal. Another could be that the object's brightness evolution influenced by phase angle and distance yield size and activity estimates that shift as geometry changes, creating a moving target for expectation. Geometry sets the stage for later discussion of activity and physical properties, but it must be completed on its own terms. At this stage, the object is still treated as a point mass for motion and a point source for light, with the understanding that both are approximations. The point mass approximation holds well for the orbit because the object is small compared with orbital distances. The point source approximation holds only to the degree that the object lacks an extended coma. If a coma exists, the light comes from a cloud as well as from a nucleus, and the cloud's shape can depend on solar radiation and the solar wind. Yet even then, the approach geometry remains the frame that determines how that cloud is seen from Earth and how its light is measured. In the approach, geometry, one more subtle influence is the distribution of observation times. Ground-based observatories can only observe at night, and the object may be visible only for part of the night, depending on its altitude above the horizon. Weather and moonlight further restrict observations. These constraints can create gaps in the data, and gaps can interact with geometry. If the object's path crosses a dense star field near the Milky Way, astrometry becomes harder, and errors increase. If the object's apparent motion is fast, exposures may trail, reducing position accuracy. If the object is very faint, longer exposures are required, but longer exposures can also blur a fast-moving source. Survey pipelines balance these factors, and the balance affects orbit quality in the early phase. By the end of this region, 3I Atlas is best described through a stable set of geometric facts and uncertainties, an incoming direction, a trajectory relative to the Sun, a predicted path through space, and a set of observation constraints that shape what can be measured. Quietly defying expectations in this context does not require any extraordinary claim. It can describe the simple experience of fitting an orbit under challenging geometry, where each new observation refines speed and direction in small increments, and where the object's behavior is measured as a set of parameters that resist early simplification. The geometry is the outer shell of the story's inner layers, and it must be held steady before any deeper physical discussion can be responsibly made. To describe 3I Atlas as interstellar is to make a claim about its relationship with the Sun's gravity at the largest scale, not about what it looks like in a telescope image. The interstellar criterion is fundamentally dynamical. It rests on whether the object is bound to the Sun. A bound object has a closed orbit, meaning that in the absence of strong perturbations, it will return. An unbound object follows an open trajectory and will pass through once leaving again. In practice, the distinction is made through measured motion and a careful choice of reference frame. This region therefore stays with classification and with the disciplined way astronomers decide what an orbit implies. The first element is energy. In the simplest two-body approximation, an object orbiting the Sun has a specific orbital energy which can be positive, negative, or near zero. Negative energy corresponds to an ellipse positive energy to a hyperbola and near zero to a parabola. Real solar system motion is not exactly two-body because planets perturb the path, but the concept still guides classification. When an orbit is computed from astrometric data, the best fit parameters imply a value for eccentricity and also imply a speed that the object would have if it were far from the Sun before the Sun's gravity accelerates it. That far distance value is often described as the asymptotic speed or velocity at infinity. If that asymptotic speed is greater than zero with high confidence, the object is unbound. Confidence is the key word. Orbit solutions carry uncertainties. Every astrometric measurement has an error bar, and systematic effects can shift many measurements together. A short observational arc can make uncertainties large. Therefore, the interstellar label is not applied solely because eccentricity is greater than 1 in an early solution. It is applied when repeated solutions updated with more data continue to show an unbound path, and when the solution remains unbound in a barycentric frame where planetary motions are more cleanly accounted for. A heliocentric orbit can appear slightly hyperbolic because of gravitational interactions with planets, especially if the object is observed after a close planetary passage. In that case, the hyperbola can reflect an energy boost gained within the solar system, not an origin outside it. Such objects are rare but possible. To claim interstellar astronomers, therefore look at the inbound path before strong planetary interactions, and at the barycentric energy ensuring that the object is unbound on the way in, not only on the way out. For 3I Atlas, the classification process begins with the best available orbit and continues with checks. The checks include testing whether the orbit remains hyperbolic when different subsets of data are used. If one observatory's data are biased, removing them can change the solution. A robust interstellar classification should not depend on a fragile subset. Another check is to examine the residuals. If the residuals suggest non-gravitational acceleration, and if that acceleration is not included in the orbit model, the fitted orbit can become biased. A small acceleration can mimic a slightly different eccentricity. Therefore, if the object is active, the classification may require an orbit model that includes non-gravitational terms, or at least an assessment of whether plausible outgassing could alter the energy estimate enough to affect the bound versus unbound conclusion. This does not mean outgassing can easily turn a bound orbit into an unbound one. It means that for marginal cases, it can shift the numerical fit. Another part of the interstellar criterion involves the incoming direction and the statistical likelihood of such an object being ejected from the solar system versus arriving from elsewhere. A solar system object on a very long period orbit perturbed by the giant planets can be placed onto a hyperbolic-looking path in a heliocentric frame, but such cases typically still appear bound in a barycentric frame when properly analyzed. The reason is that planetary perturbations redistribute energy within the solar system, rather than adding energy from outside. When an object arrives from interstellar space, its inbound direction and speed reflect the combined motion of the object through the galaxy and the sun's motion relative to the local standard of rest. In practical terms, astronomers look at the radiant, the inbound direction, and the asymptotic speed in a barycentric frame. They compare these to expectations for interstellar visitors, which are still uncertain because the sample is small. The comparison is not a proof of origin, but it is a consistency check. Quietly defying expectations at the classification level can arise from the narrowness of the boundary. If 3I Atlas sits near the threshold with eccentricity only slightly above 1 within errors, then each new set of observations can shift the classification confidence. The object could remain unbound, but with a small excess speed, making it harder to distinguish from a long-period solar system comet that has been strongly perturbed. Another possibility is that the object is clearly unbound, but its inbound speed is lower than typical naive expectations for interstellar visitors. That would not violate physics. It would simply indicate that the distribution of interstellar speeds includes slower members, or that the object's motion relative to the Sun happens to align in a way that reduces the measured excess speed. With a small sample of known interstellar objects, expectations can be shaped by a few cases, and each new case can broaden the perceived range. Classification also relies on consistent naming and reporting. The designation with an interstellar marker is assigned by official bodies based on criteria. Those criteria depend on the orbit determination and on community verification. The process is conservative because the label carries scientific weight. It affects how observing time is allocated and how the object is discussed. Therefore, the interstellar tag is not just a headline. It is a statement that the orbit as measured is unbound in a robust sense. In this region, the emphasis remains on that robustness, not on speculation about origin systems or intent. A measured unbound orbit is sufficient for the category. The underlying physics is familiar. An object from interstellar space enters the solar system with a velocity relative to the Sun. As it falls inward, it speeds up. At perihelion, it reaches a maximum speed, then it slows as it climbs back out. The path is symmetric in an ideal two-body case, but planetary perturbations and non-gravitational forces can break symmetry slightly. The object's trajectory is a natural consequence of gravity. The surprise, if any, lies not in the mechanics, but in the rarity. Interstellar objects are expected to be present in the galaxy in great numbers, ejected from forming planetary systems and from later dynamical interactions. Yet they are hard to detect because they are small and dark, and because they move quickly through the inner solar system once they are close enough to be seen. Survey sensitivity and sky coverage limit discovery. Therefore, when one is found, it can feel as if it arrives unexpectedly, even though the population may be large. The expectation gap is an observational one. For 3I Atlas, the classification stage also intersects with practical observing strategy. If the object is likely interstellar, astronomers may prioritize measurements that reduce the key uncertainties, high-precision astrometry, over a longer baseline observations that confirm or refute coma presence, and spectroscopy that might reveal gas species if activity exists. But in this region, the classification itself remains separate from physical interpretation. The interstellar label is not a claim about composition, structure, or behavior beyond the orbit. It is a claim about trajectory. A careful description must also hold a boundary between what is known and what is not. The orbit can show that the object is unbound. That does not identify its origin star system. Tracing an interstellar orbit back through the galaxy is difficult because the object and the stars it might have encountered both move under the galaxy's gravitational field, and small uncertainties grow over time. Stellar encounters and gravitational perturbations can scramble paths over long durations. Therefore, while it is possible to estimate a past direction and speed, it is rarely possible to point to a specific star with confidence. The object's origin remains broadly uncertain even when its interstellar nature is secure. This is an important quiet fact. The classification answers one question cleanly and leaves a larger one open. In the end of this classification region, 3I Atlas is defined by a measured relationship to the Sun's gravity. If it is interstellar, it is not here to stay. If it is bound, it is still part of the solar system's long-period population, and it may be visiting after a long absence. Either way, the decision rests on geometry and energy tested against uncertainty. Quietly defying expectations can mean that the orbit refuses to settle quickly, or that it settles into a category that stretches the current sample's range. The scientific posture remains the same: measure, model, test, and state confidence without excess. Beyond the orbit and its classification, lies the broad environment that acts on 3I Atlas as it travels inward. In the widest sense, the object moves through a field of forces dominated by gravity, but the environment is not only gravitational. It includes sunlight, which carries momentum and can exert a small pressure. It includes the solar wind, which is a flow of charged particles that carries magnetic fields outward. It includes the gravitational fields of the planets, which change with time as the planets move. It also includes the geometry of the object itself, because the same external influences can have different effects depending on surface properties, shape, and rotation. In this region, the attention stays with the surrounding forces and how they are expected to act on a small body at large distances before the story moves further inward into the object's own physical properties. Solar gravity is the principal force. It sets the overall trajectory. At distance, the gravitational acceleration is small, but it is steady. It also defines an escape speed, the speed needed to leave the sun's pull from a given distance. This is why interstellar classification is framed in terms of energy and asymptotic speed. But gravity is not acting alone. Sunlight pushes. The effect is tiny, yet for a very small, low-mass object with a large area relative to its mass, radiation pressure can matter. Radiation pressure depends on how much light is absorbed or reflected. A dark surface absorbs more and therefore experiences a pressure that is still present, because absorption transfers momentum. A reflective surface reflects photons and can experience a slightly different effective push. For most kilometer-scale bodies, the effect is negligible for orbit determination over short times. For very small objects, it can be measurable. In practice, if an orbit fit requires a small acceleration away from the sun, radiation pressure is one candidate, but it must be consistent with the object's estimated size and mass. Another influence from sunlight is heating. Heating is not a force directly, but it drives processes that can produce forces. As sunlight warms a surface, volatile ices can sublimate. The escaping gas can act like a jet, producing non-gravitational acceleration. This acceleration depends on the rate of gas release, the directionality of the flow, the distribution of active patches on the surface, and the object's rotation. At large distances, heating is weak, so only the most volatile substances are expected to sublimate strongly. Carbon monoxide and carbon dioxide are more volatile than water. They can drive activity farther from the sun. Yet whether they do so depends on whether they are present near the surface, whether they are trapped beneath a layer, and whether pathways exist for gas to escape. A body can contain volatiles, yet appear inactive if a dust mantle insulates the ice or if the surface is sealed by refrozen material. The solar wind influences charged material. When gas is ionized, meaning its atoms or molecules lose electrons, it becomes charged and interacts with magnetic fields. Ion tails in comets are shaped by this interaction, often pointing in a direction that reflects the solar wind flow rather than purely away from the sun. Dust tails, by contrast, are shaped more by radiation pressure and by the initial velocities of dust grains as they leave the nucleus. In a weakly active object, a clear tail may not be visible, but subtle structures can exist. At great distances and low activity levels, the ionization rate may be low and the ion tail may be faint. Observationally, the solar wind's role becomes clearer when the object is close enough for a detectable coma and when observations are deep enough to see morphology. In this region, the solar wind is part of the environment that can shape what later imaging might reveal, but it does not yet dominate the measurement story. Planetary perturbations are another environmental influence. The giant planets, especially Jupiter, can change the object's path. The magnitude of the perturbation depends on closest approach distance, relative speed, and geometry. In a close encounter, the planet's gravity can bend the trajectory noticeably. Even in a more distant encounter, it can shift the future track by an amount that matters for prediction. When astronomers compute the orbit, they include the known planets as gravitational sources. Yet uncertainties in the object's current position and velocity mean that the predicted future encounters also carry uncertainty. If an encounter is possible within the prediction window, it becomes a region of heightened sensitivity in the calculations. This is a standard feature of solar system dynamics. It can make an orbit appear to adjust as more data arrive, when in fact, the solution is simply becoming more precise as it approaches a sensitive point. There are also small forces tied to the object's own thermal behavior. One is the Yarkovsky effect, a tiny acceleration caused by anisotropic thermal emission. As a rotating body warms in sunlight and re-radiates heat, it emits infrared photons. If emission is not symmetric, a small net force results. This effect can alter the orbits of small asteroids over long times. For a newly discovered object on a fast passage, the Yarkovsky effect is usually too small to matter on the timescale of weeks or months, and it is difficult to measure directly. For an interstellar object passing through, once the cumulative effect during its solar system transit is likely negligible for orbit classification unless the object is very small and the passage is long. Still, it belongs to the catalog of environmental influences and serves as a reminder that non-gravitational forces can arise from ordinary physics. Another relevant concept is the object's response to outgassing in a statistical sense. Outgassing can be continuous or episodic. It can be dominated by one jet or many. It can change as the sun-facing side rotates into view. These patterns create time-dependent forces. Orbit solutions that include non-gravitational parameters often assume a smooth dependence on distance from the sun, but real outgassing can deviate from smoothness. If 3I Atlas is weakly active and the activity is patchy, the resulting acceleration could vary in time. This could make residuals harder to fit with simple models, creating the appearance of behavior that does not settle into the usual patterns quickly. Quietly defying expectations can thus mean that the environmental forces, while ordinary, combine in a way that produces a subtle, persistent mismatch with the simplest assumptions. The interstellar medium itself is part of the environment, but within the heliosphere, its direct influence is small compared with solar gravity and radiation. Gas density is too low to produce significant drag on a macroscopic object. Dust impacts occur, but the rate is low and the momentum transfer is tiny. Over very long times, such effects can matter for surfaces. Over the short timescale of observation, they are not primary drivers of motion. Therefore, the environment that matters now is the sun's field of gravity, and light the solar wind, and the gravitational pull of planets. Observation adds another layer of environment, one that is not physical but practical. When an object is faint, measurement uncertainty can dominate. An apparent deviation in motion can be a measurement artifact. An apparent change in brightness can be an artifact of changing sky conditions. In this sense, the environment of observation includes atmospheric seeing, sky background, brightness, moonlight, and the presence of nearby stars. If the object passes through a crowded field, background subtraction becomes harder and photometry becomes less reliable. Photometry is the measurement of brightness. In crowded fields, faint background stars can blend with the object's light, causing it to appear brighter. As the object moves, that blending changes, creating spurious variability. These effects can mimic or mask real changes. Therefore, a careful approach treats early brightness variations with caution and seeks confirmation across multiple datasets. The phrase quietly defying expectations can also be linked to the balance between sunlight-driven forces and gravitational forces at the distances of interest. For a typical comet, outgassing increases as it approaches the Sun, and non-gravitational acceleration becomes more noticeable closer in. If 3I Atlas shows a measurable deviation earlier than expected, it could indicate the presence of more volatile ices or an unusually exposed volatile layer. Alternatively, if it remains remarkably consistent with a gravity-only model even when faint activity is suspected, it could suggest a low level of gas release or a geometry in which jets cancel out in the net acceleration. Both outcomes are plausible. Both are quietly consistent with ordinary physics. The interest lies in which combination the data support. In this region, the object is still treated as a traveler within a field subject to external influences that can be enumerated and bounded. The next inward steps will involve the light curve spectra and properties of the object itself. Before that, the environmental frame must remain clear. Gravity shapes the main path. Sunlight warms and pushes. Gas release, if present, can add gentle thrust. The solar wind shapes charged outflows. The planets perturb the route. Observational conditions shape what is measured and how confidently it is interpreted. When expectations are challenged, the first interpretation is not to replace physics, but to check which part of this environment, physical or observational, is being underestimated. Light is the first physical evidence of 3I Atlas that can be studied in detail, and it remains the most continuous stream of information as the object moves. In this region, attention stays with what the brightness and its variations can tell without yet assuming a specific surface, a specific composition, or a specific internal structure. The object is still far enough and small enough that it is often unresolved, meaning even large telescopes see it as a point spread over a few pixels. Yet within that limitation, careful photometry can reveal patterns. Those patterns are the quiet language of rotating bodies, evolving coma, and changing viewing geometry. The most basic quantity is apparent brightness, the amount of light received by the telescope. Apparent brightness changes with distance from Earth and distance from the Sun. It also changes with phase angle, the Sun object-observer angle, because the visible fraction of illuminated surface and the scattering behavior of surface materials both depend on geometry. To compare observations taken at different times, astronomers often correct brightness to a standard geometry. They compute an absolute magnitude, which is the brightness the object would have if it were at a standard distance from both the Sun and Earth, and at a reference phase angle. This correction is model-dependent. It assumes a phase function, a relationship between brightness and phase angle. Different surfaces and different comae have different phase functions. Therefore, even corrected brightness contains some uncertainty. Still, the correction helps separate changes caused mainly by distance from changes caused by intrinsic evolution. For small bodies, a key signature in brightness is periodic variation. If the object rotates and has an elongated shape or an uneven surface reflectivity, the amount of light it reflects changes as it turns. This creates a light curve, a plot of brightness versus time. A repeating pattern suggests a rotation period. The amplitude of the variation, how much it brightens and dims, can suggest how elongated it is, or how strongly surface reflectivity varies. However, a coma complicates this. If the object is active and surrounded by dust, the coma can add a steady glow that reduces the relative amplitude of rotational variation. It can also vary on its own, creating brightness changes not tied to rotation. Therefore, interpreting a light curve requires an assessment of whether the object is purely a bare nucleus-like body or whether it carries an extended cloud. Observational practice begins by measuring brightness within aperture's circular regions around the object in the image. Different aperture sizes capture different amounts of coma. A small aperture emphasizes the central region and is more sensitive to nucleus light. A larger aperture captures more of the surrounding coma. Comparing brightness measured with different apertures can reveal whether the object is extended. If the brightness increases more than expected, with aperture size compared to nearby stars, it suggests the presence of extended material. This is not a definitive proof in all cases, because seeing conditions can blur stars and the object differently, but with careful calibration, it is a useful test. When multiple telescopes and nights are combined, the picture becomes clearer. Quietly defying expectations can occur when the brightness evolution of 3I Atlas does not match common patterns. A typical comet brightens as it approaches the Sun, often faster than a simple inverse square scaling because increasing activity adds extra scattering area. If 3I Atlas brightens more slowly, it could be less active, or it could have a surface that reflects light differently, or it could be observed at phase angles that suppress brightness. If it brightens faster, it could indicate early activity driven by volatile ices, or it could reflect a change in observing geometry that enhances forward scattering by dust. Forward scattering occurs when dust grains scatter light, preferentially in the direction of travel of the light, making comae appear brighter at certain phase angles. This can cause a dust-rich object to brighten strongly when viewed at large phase angles, even if gas production is not high. Therefore, unusual brightening is not necessarily unusual physics. It can be a natural consequence of dust scattering and geometry. Brightness can also change because of fragmentation or outbursts. Some comets experience sudden releases of dust and gas when surface layers crack or when trapped volatiles suddenly escape. These events can produce a noticeable jump in brightness. If such a jump occurs, it can be measured photometrically and then checked for morphological changes in images. Yet outbursts can be subtle if the object is far away and the event is small. They can also be masked by observational noise. Therefore, claims of outbursts require consistent confirmation across multiple observations and careful attention to background contamination. Background contamination is a central concern in photometry. When the object passes near a star in the image, the star's light can blend with the object's light, making it appear brighter. As the object moves, the blending can change, creating apparent variability that is purely geometric in the sky plane. Surveys mitigate this by modeling and subtracting background sources, but subtraction is never perfect at faint levels. Deep follow-up observations can avoid crowded fields or can use higher resolution imaging to separate sources. Still, for a faint moving object, some degree of contamination risk remains. Therefore, a quiet, restrained description keeps this in mind when interpreting brightness fluctuations. Color photometry adds further constraints. If brightness is measured through 2 or more filters, the differences can indicate whether the light is dominated by a bare surface reflection or by dust and gas emissions. Many cometary gases emit light in specific bands, and certain filters may capture these emissions more than others. Dust generally produces a more continuous reflection spectrum, often with a slight reddening, meaning it reflects more efficiently at longer wavelengths. A surface that has been processed by space weathering can also appear red. Therefore, a red color can come from dust or from surface materials. A neutral color can suggest different mixtures. Yet color measurements are sensitive to calibration and to the choice of aperture because coma color can differ from nucleus color. If the coma dominates, the color reflects dust and gas rather than the nucleus. If the nucleus dominates, the color reflects the surface. Separating these requires careful observational strategy. Time sampling shapes what can be inferred. A rotation period can be measured only if observations cover enough time to see repetition. If the period is long, it may require observations over multiple nights. If the object's brightness is changing due to distance and activity, at the same time the rotation signal must be disentangled from the overall trend. This is done by modeling the long-term brightening and then looking for periodic residuals, or by using techniques that search for periodicity in unevenly sampled data. The result is not always unique, and multiple candidate periods can fit. The uncertainty can be reduced by combining datasets, but differences in filters and calibration between observatories must be handled carefully. A particular complication arises if the object is not rotating about a single stable axis. Some small bodies tumble rotating in a complex, non-principal axis state. Tumbling produces light curves that are not simply periodic, or that show multiple periods. It can result from past collisions or from torques due to outgassing. If 3I Atlas shows a light curve that resists a simple single-period fit, tumbling is one natural possibility. Another possibility is variable activity that changes the brightness in a way that mimics irregular rotation. Distinguishing these requires both photometry and imaging, and it may remain uncertain. At the level of light alone, the most responsible approach is to build a hierarchy of explanations that remain within ordinary physics and within observational constraints. Geometry accounts for some changes. Rotation accounts for periodic variation. Dust scattering and gas emissions account for deviations from bare surface expectations. Background contamination accounts for some apparent variability. Outbursts and fragmentation account for sudden changes if they are confirmed by morphology. Each explanation has signatures, and each can be tested. Quietly defying expectations can mean that the object's light curve sits in an unusual combination of these factors, such as a low-amplitude variation, suggesting either a round body or a coma that hides rotation, combined with a brightness trend that does not align with typical comet activity at the measured distances. In this region, 3I Atlas remains primarily a measured light source. Its brightness becomes a record of its interaction with sunlight and its own rotation filtered through Earth-based observation conditions. The light does not announce causes on its own. It provides constraints. The next inward steps can use these constraints to narrow down physical size, shape, and activity mechanisms. But for now, the discipline is to let light be what it is. A steady, quantifiable stream of photons whose variations, when handled carefully, can reveal the quiet, measurable behavior of a small body moving through space. Beyond brightness patterns, the next layer of evidence in the outward to inward path is the distribution of light by wavelength and the way that distribution is recorded by instruments. This is the realm of spectra, the measured intensity of light as a function of wavelength and of multi-band observations that approximate a spectrum by sampling it in a few broad regions. For 3I Atlas, spectral information is not automatically available at discovery. It requires targeted observing time and sufficient brightness. When it is obtained, it does not provide a complete chemical inventory. It provides constraints often sparse that must be handled with care. In this region, the focus stays with what spectra can reveal at a broad level and with the limitations that keep many conclusions tentative. A spectrum begins with light collected by a telescope and dispersed. Dispersion is the separation of light into its component wavelengths, often using a grating or prism. The resulting measurement can show a smooth continuum reflecting sunlight scattered by dust or a surface, and it can show emission features, narrow peaks at specific wavelengths produced when molecules in gas are excited and emit photons. For comets, emission features often come from radicals and fragments produced when sunlight breaks larger molecules apart. For example, water does not always show directly in optical spectra, but its photodissociation products can be detected. Carbon-bearing species can show in various bands. In the infrared, different molecules have characteristic vibrational signatures. In the radio, certain molecules emit at specific frequencies. Each wavelength region offers different windows, yet each has different sensitivities and different challenges. If 3I Atlas shows no obvious emission lines, its spectrum may be dominated by reflected sunlight. In that case, the spectrum can be compared to the solar spectrum, and the difference called the reflectance spectrum can reveal whether the object is redder or more neutral than sunlight. A red reflectance slope means the object reflects more efficiently at longer wavelengths. Many small bodies in the outer solar system show red slopes, often linked to complex organic residues and long-term irradiation effects. But the same appearance can also be produced by fine dust in a coma. Therefore, a red slope by itself does not uniquely identify surface composition. It indicates that the scattering material, whether dust grains or surface regolith, has wavelength-dependent reflectivity. Regolith refers to a layer of loose material covering solid rock or ice. On small bodies, regolith can be dust and fragments produced by impacts and thermal stress. If a coma exists, the scattering material can be freshly released grains, not long-settled regolith. Emission features, if present, would indicate gas. Gas implies active sublimation or release of volatile material. The distance from the Sun at which gas becomes detectable depends on both the intrinsic production rate and the sensitivity of the instruments. Far from the Sun, only highly volatile species are expected to sublimate significantly. Carbon monoxide and carbon dioxide are common candidates for distant activity. However, carbon dioxide is difficult to observe from the ground in certain bands because Earth's atmosphere absorbs strongly. Space-based infrared telescopes are better suited. Carbon monoxide can be observed in radio and infrared, but it requires dedicated facilities. Water becomes dominant closer in, but water itself is often inferred rather than directly measured in optical. Therefore, the absence of detected gas lines does not guarantee inactivity. It may only reflect observational limits. Quietly defying expectations at this level can mean that the spectrum does not match the most familiar patterns. If 3I Atlas is interstellar, a natural question is whether its composition looks broadly similar to solar system comets. It might because the chemical building blocks of planet formation are thought to be widespread. It might differ because the conditions in its parent system could have produced different ratios of ices and dust. Yet with sparse data, differences can be subtle. A slightly different spectral slope or a weak feature can suggest difference without proving it. The correct posture is to state what is detected and what is not detected, and to note the sensitivity thresholds when they are known. Instrument limitations shape these statements. A spectrum of a faint object can have low signal-to-noise ratio. Signal-to-noise ratio is the strength of the desired signal compared to random variations from noise sources like detector rateout, sky background, and photon counting statistics. Low signal-to-noise can hide weak features or produce apparent features that are not real. Sky subtraction is a major challenge, especially in the near-infrared where the sky glows. Calibration is another. To measure reflectance, observers compare the object's spectrum to that of a solar analog star and correct for atmospheric transmission. Small errors in these steps can alter the slope and create artifacts. Therefore, claims of subtle spectral features require verification across nights or instruments. Multi-band photometry is a related tool. Instead of dispersing, light observers measure brightness through several filters. The differences between filters approximate the spectral shape. This is less detailed than spectroscopy, but it can be obtained for fainter objects. It can indicate whether the object is unusually red, whether it has a steep ultraviolet drop, or whether it shows excess in bands that might contain emission lines. In comet studies, certain narrowband filters are designed to isolate specific emission features, but wide-field surveys often use broader filters. Broad filters blur line information into the continuum. Still broad colors can sometimes suggest the presence of gas if an emission band falls strongly within one filter and not the other. Such inferences remain tentative without spectroscopy. Another wavelength region that can matter is thermal infrared. In thermal infrared, the object emits heat rather than reflecting sunlight. Thermal emission depends on size, temperature, and surface properties, like thermal inertia, which is the resistance of a material to temperature change. A surface with low thermal inertia heats and cools quickly, while high thermal inertia changes more slowly. Thermal measurements can help break the degeneracy between size and albedo. An object can be bright because it is large or because it is reflective. Thermal emission depends more directly on size, so combining reflected light and thermal emission can constrain both size and albedo. For distant faint objects, thermal measurements are challenging and often require space-based telescopes. If such data exist, they can be powerful. If they do not, size remains uncertain. Radio observations can also contribute, particularly for gas detection. Certain molecules have rotational transitions that emit radio lines. Detecting these lines can provide direct evidence of outgassing and can estimate production rates. But radio telescopes have limited time and require accurate ephemerides predictions of where the object will be in the sky. If the orbit is still uncertain, pointing becomes difficult. Also, the object must be producing enough gas for detection. Therefore, radio non-detections are common and must be interpreted as upper limits. In the context of quietly defying expectations, one common pattern is that early spectral attempts yield only a featureless continuum. This can be surprising to those expecting a bright comet-like spectrum, but it is normal for faint or weakly active bodies. Another pattern is that the spectral slope appears unusual compared with typical solar system comet dust. Yet the overlap between populations is large, and a slope difference can arise from grain-size distribution in the coma. Fine grains scatter differently than coarse grains. The size distribution can change with distance and with activity mechanism. Therefore, a spectrum that looks different may reflect dust physics rather than a fundamentally different chemistry. In this region, the core scientific focus is evidence handling. A detection of a line implies gas. The identification of a line requires matching wavelength and considering alternative sources and calibration artifacts. The strength of a line can estimate abundance, but it depends on excitation conditions and on models. A continuum slope implies a certain scattering behavior. Interpreting that slope requires separating nucleus light from coma light and correcting for observing effects. Thermal data constrain size, but only with assumptions about emissivity, a measure of how efficiently a surface emits thermal radiation. Each inference is conditional. 3I Atlas, if it is truly interstellar, is of special interest because it offers a rare opportunity to sample material formed around another star. Yet the spectral region does not turn that interest into certainty on its own. It offers a careful set of constraints that can confirm activity, suggest broad material classes, and narrow size and albedo estimates. Quiet defiance of expectations can be as simple as a spectrum that stays stubbornly plain, forcing patience, or as subtle as a hint of emission that appears and disappears with changing geometry and sensitivity. In all cases, the proper description remains calm and bounded. The light is measured. The instruments shape what can be known. The conclusions remain anchored to detection limits and to repeatable features. Having established how light and wavelength constrain 3I Atlas, the next inward step is activity in the surrounding space immediately around the body, the coma region. A coma is not a solid structure. It is a cloud of gas and dust that forms when material leaves the surface. It is shaped by sunlight, by the object's gravity, which is usually very weak by gas flow and by external forces like radiation pressure and the solar wind. In this region, the focus stays with the coma as a global envelope and with the basic evidence for outgassing and dust release without yet narrowing to the nucleus itself. Activity begins with heat. Sunlight warms the surface. If volatile material exists near the surface, it can sublimate. The gas that forms is initially constrained by the porous structure of surface layers. It moves through tiny channels and fractures. When it escapes into vacuum, it expands rapidly. In doing so, it can drag dust grains with it. Dust grains range from fine particles comparable to smoke to larger grains closer to sand. The balance depends on gas pressure, surface cohesion, and the availability of loose material. The resulting mixture of gas and dust forms the coma. The coma's appearance depends on how much material is released, how fast it is released, and how sunlight interacts with it. For observers, the first sign of a coma is often a subtle broadening of the object's image compared to nearby stars. Stars are effectively point sources, and their light is spread by the telescope optics and by the atmosphere if ground-based. The object's light should match that spread if it is a bare, point-like body. If it is surrounded by a coma, the light profile becomes slightly more extended. This difference can be measured by comparing the full width at half maximum of the object and nearby stars, or by comparing how brightness grows with increasing aperture size. If brightness grows more than expected, as the aperture expands, it suggests extended material. These are careful tests, not dramatic ones, and they can be affected by seeing and by tracking errors. Therefore, repeated measurements under varied conditions are used to build confidence. A coma can be present even when it is not easily visible. If the coma is small and faint, it may be hidden within the seeing disk of the atmosphere. If dust production is low, the coma's surface brightness can fall below the background. Yet even a small coma can matter physically because it implies ongoing mass loss and because it can affect astrometry. It also matters because it is one of the most direct pathways to non-gravitational acceleration. Gas leaving the surface carries momentum, and the nucleus recoils. That recoil is the basis for small changes in the orbit beyond gravity alone. Quietly defying expectations in the coma region can mean that the evidence for activity is ambiguous, subtle, or inconsistent with the most common distance-based expectations. For a typical solar system, comet activity is expected to increase as it approaches the Sun. At large distances, water ice is usually too cold to sublimate strongly. Therefore, distant activity, if present, often points toward more volatile ices or toward mechanisms that expose volatiles intermittently. If 3I Atlas shows hints of activity farther out than expected for water-driven comets, it could be consistent with carbon monoxide or carbon dioxide sublimation, or with the release of trapped gas through cracks. Another possibility is that the object carries a layer of supervolatile material near the surface because it has not been warmed before in the solar system. An interstellar visitor could arrive with volatiles preserved near the surface if it has remained cold for a long time, but it could also arrive with a processed, insulated surface. Both outcomes are plausible. The coma region allows these possibilities to be tested by measuring when activity begins and how it evolves. The morphology of the coma, if it can be imaged, provides additional constraints. A symmetric coma suggests relatively uniform outgassing or dust release from many locations. An asymmetric coma suggests localized jets where active patches produce directed flows. Jets can form when sunlight illuminates a specific area that contains exposed ice or when gas finds a preferred pathway through a fracture. As the object rotates, jets can sweep through space and create spiral or fan-like structures. These structures are faint and require high-quality imaging. If such structures are present, they can link to rotation period and to the distribution of active areas. If they are absent, activity may still exist, but be too weak or too diffuse to show structure. Dust tails are shaped by radiation pressure. Once dust grains are released, sunlight pushes on them. Smaller grains feel proportionally more push relative to their mass and are accelerated more strongly away from the sun. Larger grains move more slowly and stay closer to the object's orbit. Over time, dust released at different times forms a tail that can curve along the orbit. The tail's direction and curvature can be analyzed to infer dust grain sizes and emission times. In weak activity, a tail may not be visible, or it may appear only in deep stacked images. In such cases, the coma can still be present without a clear tail. Ion tails, when present, are shaped by the solar wind and magnetic fields. They tend to point more directly away from the sun and can show rapid changes as solar wind conditions fluctuate. Detecting an ion tail requires enough gas and enough ionization. For a faint, distant object, this is often beyond reach. Therefore, the coma region is often dominated by dust diagnostics rather than ion diagnostics in early stages. Quantifying activity involves measuring the coma brightness relative to the nucleus. One common approach is to compute a parameter that relates dust production to observed brightness within a certain aperture. This parameter depends on assumptions about dust properties and is best treated as a comparative measure rather than an absolute physical production rate. Gas production, if measured through spectroscopy, can provide more direct rates, but it depends on excitation models and on how gas is distributed. For many objects, early activity measures are upper limits rather than detections. In 3I Atlas, the notion of defying expectations can also arise if the coma behavior does not align with the orbit-derived prediction of solar distance. If the object is at a distance where strong coma activity is not expected, yet photometry suggests extended scattering area, observers must consider whether the apparent coma is real. Background contamination and seeing effects can mimic extension. Therefore, confirming a coma often involves multiple techniques, comparing profiles, stacking images, observing in different filters, and checking whether extension persists across nights. If extension persists, activity becomes more plausible. Another subtle effect is that dust can persist after a weak outburst, creating a faint coma even if gas release has decreased. Dust grains can remain near the nucleus region for a time, especially larger grains with low acceleration. If activity is episodic, the coma can appear to turn on and off. This can produce brightness variations that complicate interpretation. A steady orbit deviation combined with a variable coma could suggest that outgassing is intermittent, but still produces a net force over time. Alternatively, it could indicate that the orbit deviation is not real and arises from coma-induced astrometric shifts. These are competing explanations that require careful data to separate. Within the coma region, the most grounded statement is that activity, if present, provides a physical mechanism for both brightness changes and small deviations in motion. It also provides a pathway to infer something about the object's near-surface volatile inventory. Yet it does not by itself identify which volatiles are involved unless gas is detected. A coma can be dust-rich and gas-poor in detectability. It can also be gas-rich, but too faint for detection. Therefore, uncertainty remains a core part of the description. In a calm narrative voice, the coma is treated as a measured envelope shaped by external and internal factors. It is not a sign of intention or anomaly. It is a common outcome of heating a cold, volatile-bearing body in sunlight. If 3I Atlas is quietly defying expectations, it may be doing so by placing that common process at an uncommon distance, by producing an envelope that is just at the edge of detectability, or by combining weak activity with measurable dynamical effects that challenge simple models. The discipline is to let the envelope be described by its measurable properties, extent, symmetry, brightness, color, and how these change with time and distance. This completes the move from broad observational light to the immediate physical surroundings of the object, preparing for the next step inward, where deviations from gravity-only motion are examined with greater specificity. The orbit of 3I Atlas is a prediction of where it should be under gravity. When observations show a consistent structured difference from that prediction, the difference is described as a non-gravitational acceleration. In this region, attention stays with how such an acceleration is detected, modeled, and bounded. The focus is not on an assumed cause. The focus is on measurement practice and on the set of natural mechanisms that can produce small accelerations in small bodies. Quietly defying expectations can be expressed as the difficulty of fitting a stable model, or as the presence of a measurable acceleration where it is not usually prominent. Non-gravitational acceleration is not measured directly as a force. It is inferred from residuals in astrometry. Astrometry provides sky positions at known times. A gravitational model predicts positions. The residuals are the differences. If residuals are random and small, the gravitational model is sufficient. If residuals show a systematic drift, such as the object repeatedly appearing ahead of the predicted position along its track, the drift can indicate acceleration. The acceleration can have components radial directed away from or toward the Sun, transverse along the direction of motion, and normal perpendicular to the orbital plane. In practice, orbit solvers can fit these components as parameters that, when added to the model, reduce residuals. A key part of this process is the dependence of the acceleration on distance from the Sun. For outgassing-driven acceleration, the effect generally increases as the object approaches the Sun, because heating increases sublimation. Orbit models often include a function that scales with solar distance based on empirical or semi-physical representations of how sublimation varies. The most commonly used functions are tuned to water ice, because many comets are water-driven in the inner solar system. For distant activity, water functions may be inappropriate. If the object is active due to carbon monoxide or carbon dioxide, the distance dependence can differ with activity possible farther out. Therefore, the choice of scaling function matters. If an orbit solution uses a water-based model for an object whose activity is driven by different volatiles, the fitted parameters may not capture the true behavior, and residual patterns may remain. Another difficulty is that outgassing can be anisotropic. If gas leaves uniformly from the sunlit hemisphere, the net thrust points roughly away from the Sun. If it leaves from a localized patch, the thrust direction can vary with rotation. Over many rotations, the net effect can average out to a direction that depends on the distribution of active areas and on the rotation axis orientation. If the rotation axis is tilted, different regions receive sunlight over time, and activity can shift seasonally as the object moves along its path. For a newly discovered object, the rotation axis and activity distribution are usually unknown. Therefore, non-gravitational acceleration models are approximations. They capture a net effect, not the fine structure. The data themselves also have limitations that can mimic acceleration. If a coma is present and asymmetric, the measured center of light may not match the nucleus. Astrometric pipelines often assume a point-like source. If the coma adds a tailward brightness extension, the centroid can shift slightly. This shift can produce residuals that look like acceleration. The effect can vary with observing geometry and with coma evolution. Therefore, confirming a true dynamical acceleration requires checks that reduce the influence of coma-induced centroid bias. These checks can include using larger telescopes with better resolution, using techniques that model the coma and try to locate the nucleus position, or selecting only observations where the object appears most stellar. Even then, some bias can remain. Quietly defying expectations can occur when the residuals persist across many observatories and over a long-time baseline, suggesting that a non-gravitational term is needed. It can also occur when different teams fit different models and obtain different parameter values, not because anyone is careless, but because the data quality and the chosen model functions lead to different best fits. This is common in comet orbit work. As more data arrive and as the arc lengthens, the fit tends to converge. But convergence can be slow if activity changes rapidly or if the object is faint. When a non-gravitational acceleration is inferred, the most common natural cause is outgassing. Outgassing produces a recoil force. The strength of the recoil depends on gas production rate and on the speed of the gas as it leaves. Gas speed depends on temperature and molecular mass. Lighter molecules can move faster. The effect on the nucleus depends on mass. A small nucleus can experience a larger acceleration for the same thrust because acceleration is thrust divided by mass. This is why small active bodies can show measurable non-gravitational effects. Yet a high acceleration does not necessarily mean a high production rate. It can mean a low mass. Outgassing can also carry dust. Dust does not contribute much to thrust compared to gas because dust moves more slowly and is often a smaller fraction of the escaping momentum. But dust can dominate the brightness. Therefore, a bright, dusty coma does not automatically imply strong thrust, and a faint coma does not rule it out. A gas-rich, dust-poor outflow could produce thrust with little visible dust. In such cases, the acceleration could be measured without a strong optical coma signature. Conversely, a dust-rich coma could produce visible signs with modest thrust. These combinations complicate intuitive expectations and can make an object appear to behave oddly when judged only by brightness. Radiation pressure is another potential non-gravitational influence. It pushes away from the sun. For a solid body large enough to be tracked as a minor planet, radiation pressure is usually negligible. But if the object is very small, or if it has an unusually large area-to-mass ratio, radiation pressure can produce measurable acceleration. Distinguishing radiation pressure from outgassing requires comparing the direction of acceleration and its distance dependence, and considering constraints on size and mass, from brightness, and, if available, thermal measurements. In many cases, outgassing is favored because it is common and because it can produce acceleration components not purely radial. Radiation pressure is more purely radial, yet even outgassing can appear radial if averaged over rotation. Therefore, the distinction is not always clean. Another small effect is solar tidal stress and rotational changes. As an object approaches the sun, thermal gradients and outgassing torques can change its rotation rate. A changing rotation rate can alter the pattern of jets and therefore the net thrust direction over time. This can make the acceleration time variable in ways that simple models do not capture. If 3I Atlas exhibits an acceleration that changes in magnitude or direction faster than expected, one natural explanation is changing activity geometry rather than a new force. In the context of interstellar objects, non-gravitational acceleration carries additional interest because there are fewer precedents. The sample is small. Expectations are built from solar system comets and from a small number of interstellar candidates. If 3I Atlas displays a non-gravitational acceleration that is larger than typical for comets at the same distance, it could suggest a small mass, a volatile-rich surface, or a geometry that produces efficient thrust. If it displays a smaller acceleration than expected, given its brightness, it could indicate that brightness is dominated by dust with relatively low gas production, or that the coma biases photometry without strong thrust. Each interpretation remains within standard physics. The defiance of expectation is then a mismatch between simple proxies and the measured dynamical behavior. The careful way to speak about this region is to keep the chain of inference visible. The acceleration is inferred from residuals. The residuals depend on astrometry quality and on coma bias. The model depends on assumed distance scaling and on net averaging over rotation. The physical interpretation depends on mass activity and geometry, many of which are uncertain. Therefore, conclusions should be framed as bounds. A measurable acceleration implies that some combination of thrust and area-to-mass effects exists. It does not uniquely determine the mechanism without additional evidence, such as gas detections, coma morphology, or thermal constraints. This region ends with a clear, quiet understanding of what non-gravitational acceleration means for 3I Atlas. It is a measured deviation from a gravity-only path expressed in fitted parameters and refined as more data arrive. It can be explained by familiar processes, chiefly outgassing, and possibly by radiation pressure if size and mass allow. The object may appear to defy expectations because the acceleration does not align with naive brightness-based assumptions, or because the fit remains sensitive and evolving. Yet within the measured framework, it is a tractable problem. Quantify residuals, test models, and allow the data to narrow the range of ordinary explanations. Moving one step inward from the coma and from non-gravitational effects, the description narrows to the body itself as a whole physical object. In this region, the focus is on global properties that can be bounded size, shape, and mass constraints, and the way these are inferred from light and from dynamics. For 3I Atlas, these properties are not measured directly in most cases. They are inferred from indirect evidence, and each inference rests on assumptions. Quietly defying expectations can mean that the inferred size range shifts with new data, or that different methods give bounds that are hard to reconcile without careful attention to uncertainty. The most common size estimate begins with brightness. If the object is inactive and has no coma, its brightness comes mainly from reflected sunlight off its surface. The reflected light depends on cross-sectional area and on albedo. Without knowing albedo, one cannot know size uniquely. Astronomers therefore often use a plausible albedo range based on similar objects. Dark asteroids and comet nuclei have low albedos, while some icy bodies can be brighter. Using a low albedo yields a larger size for the same brightness. Using a higher albedo yields a smaller size. The resulting size estimate is a band. It is not a point value. If the object is active, brightness includes dust scattering, and the nucleus contribution can be a small fraction, making size estimates from brightness alone unreliable until activity is constrained. A second way to constrain size is through thermal emission. Thermal emission depends on surface temperature and area. If an infrared measurement is available, it can help break the albedo size degeneracy. A bright thermal signal implies a larger emitting area or a higher temperature. Temperature depends on distance from the sun and on thermal properties, but for a first-order estimate it can be bounded. Combining thermal and optical brightness allows an estimate of both albedo and size. Yet for distant, faint objects, thermal measurements are often unavailable or have large uncertainties. If thermal data exist only as an upper limit, they still provide a bound on size because an object larger than a certain size would be expected to emit more heat than observed. These bounds can be useful even when they are not precise. Shape is inferred from light curve amplitude. If brightness varies significantly with rotation, the object is likely elongated or has strong albedo variations across its surface. A large amplitude suggests a more elongated shape if the surface reflectivity is roughly uniform. A small amplitude could mean a more spherical shape, or it could mean that the rotation axis is oriented such that the object's cross-section changes little from the observer's perspective. It could also mean that coma light masks the nucleus light-reducing amplitude. Therefore, light curve amplitude alone cannot fix shape, but it can constrain plausible elongations given assumptions about viewing geometry and coma contribution. Mass is the hardest property to measure. For most small bodies, mass is not directly measured unless the object has a gravitational interaction with another body that can be detected, such as a binary companion, or unless a spacecraft visits. For 3I Atlas, mass must be inferred indirectly. One indirect approach comes from non-gravitational acceleration. If the acceleration is attributed to outgassing, and if gas production rate can be estimated from observed gas emissions, then thrust can be estimated. Given thrust and measured acceleration, mass can be estimated as thrust divided by acceleration. This approach is highly uncertain because it requires knowledge of gas outflow speed, the fraction of gas that produces net thrust, and the directionality of jets. It also requires a reliable gas production rate, which may not be available. If only dust is seen, gas production remains uncertain. Therefore, mass estimates derived this way are often broad and model-dependent. Still, they can provide order of magnitude bounds. Another indirect mass constraint involves radiation pressure. If an acceleration is consistent with radiation pressure, the required area-to-mass ratio can be computed. Given an estimated area from brightness, mass can be bounded. But again, this depends on size estimates and on assumptions about the object's structure. For ordinary solid bodies, the area-to-mass ratio is small. For very thin or porous structures, it can be larger. Without direct evidence, the safest approach is to treat radiation pressure explanations as conditional. The primary point is that if an acceleration is measured, it implies a certain relationship between force and mass, and that relationship constrains plausible combinations of size, density, and activity. Density is a derived property that requires size and mass. Comet nuclei are often low density and porous. They can be mixtures of ice and dust with void space. A low density affects how the body responds to outgassing and to tidal forces. If 3I Atlas is small and experiences measurable non-gravitational acceleration, a low density could help explain a larger acceleration for a given thrust. But density remains speculative without mass. Therefore, density is best discussed as a range consistent with known comet-like bodies rather than as a measured property. Quietly defying expectations can arise when brightness-based size estimates and dynamics-based mass constraints appear to pull in different directions. For instance, if the object appears bright but shows a strong non-gravitational acceleration, one might infer a small mass relative to apparent size, suggesting high porosity or a brightness contribution dominated by dust. Alternatively, if the object appears faint but shows little acceleration despite suspected activity, one might infer either a larger mass or a low net thrust due to symmetric outgassing. These are not contradictions. They are prompts to revisit assumptions: how much of the brightness is nucleus versus coma? What is the plausible albedo range? What is the likely activity mechanism, and how reliable is the measured acceleration? The global size-shape discussion also interacts with observational resolution. If the object is close enough and large enough, high-resolution imaging might marginally resolve it or detect an extended core within the coma. In most cases, it remains unresolved. Yet even unresolved, the point spread function contains information. Slight elongation could indicate trailing due to motion, or it could indicate a real extended source. Distinguishing these requires careful tracking and image analysis. If a resolved measurement is not possible, the best that can be done is to bound the size by what would have been resolved, given the instrument and conditions. Such bounds can be conservative and still valuable. Another subtlety is phase effects on brightness that can mimic size changes. If the phase angle changes over time, the object can brighten or dim due to scattering behavior without any change in size or activity. If this effect is not corrected accurately, size estimates derived from brightness at different times can appear inconsistent. For dusty comae, forward scattering can produce strong phase-dependent brightening, making the object appear much brighter at certain geometries. If this occurs, a naive size estimate could shrink dramatically once geometry changes, giving the impression of an object that changes size. In reality, it is the apparent brightness changing due to scattering. Therefore, global property inference must remain anchored to corrected quantities and to awareness of scattering effects. In the global body region, one more constraint can come from the stability of rotation. If a rotation period is measured and the object is inferred to be very elongated, there are limits on how fast it can spin without breaking apart given its density and cohesion. A very fast rotation would require either higher cohesion or higher density. Comet nuclei are often weak. Therefore, a fast rotation could constrain density or imply structural strength. Yet because shape and density are uncertain, these constraints are broad. Still, they provide a consistency check. The combination of size, shape, and rotation should not violate plausible material strength ranges known from small solar system bodies. This region ends with a global portrait that remains bounded. 3I Atlas has a size range implied by brightness and albedo assumptions, modified by any coma contribution. It has a shape constraint hinted by light curve amplitude modified by viewing geometry and coma masking. It has mass and density that may be weakly bounded by non-gravitational acceleration if activity is quantified, but these remain uncertain without direct gas measurements or a resolved nucleus. Quietly defying expectations in this region does not mean the object changes its physical nature. It means the data allow multiple consistent physical interpretations, and each new dataset can shift the balance among them. The correct approach is to hold each inference as conditional, to trace it back to measured quantities, and to keep the global description calm and precise as the story moves further inward into rotation stability and near-surface structure. With global size and mass bounds in place, the next inward layer is motion within the body itself, chiefly rotation and the stability of that rotation. Rotation is not a decorative detail. It shapes how sunlight is distributed across the surface, how heating progresses where sublimation can occur, and how any jets of gas and dust are oriented over time. Rotation also shapes the interpretation of photometry and the modeling of non-gravitational acceleration. In this region, the focus stays with rotation tumbling and the physical implications of spin for a small body, keeping all statements bounded by what can be inferred from light curves and by known behavior of small solar system objects. A rotation period is inferred when brightness variations repeat. For a simple rotating body with a stable spin axis and a roughly fixed shape, the light curve repeats with a characteristic period. The measured period can sometimes be ambiguous by a factor of 2, because an elongated object can present two similar maxima and minima per rotation. Careful analysis and sometimes color or phase-resolved data are used to distinguish single-peaked and double-peaked solutions. The period is rarely exact in early data because sampling can be uneven. Day-night cycles at observatories create gaps. Weather creates gaps. Combining datasets from different longitudes helps fill gaps. Even then, multiple candidate periods can fit until the dataset grows. If 3I Atlas is active, rotation analysis becomes more complex. A coma can add a steady component of light that reduces the amplitude of rotational variation. If activity is localized, the brightness can vary not only because of shape, but because a jet turns toward or away from the observer. In that case, the period inferred from brightness may reflect the rotation of the active region rather than the overall shape. If multiple active regions exist, the light curve can become irregular. Therefore, the first step is always to assess whether the object appears point-like or extended, and whether the brightness variations are consistent across aperture sizes. If the variations persist in small apertures more than in large apertures, they may be nucleus-dominated. If the variations are stronger in large apertures, they may involve coma changes. Rotation also interacts with the sun through torque. When gas leaves the surface, it applies a reaction force at the site of emission. If the emission is not symmetric, it can change the object's spin rate or spin axis. This is analogous to how a thruster can rotate a spacecraft. Over time, such torques can spin a small body up or down. For comet nuclei, outgassing torques have been observed to change rotation periods measurably over a single apparition in some cases. This means that rotation is not always constant. If 3I Atlas shows a light curve whose period seems to drift over time, one natural explanation is change in spin due to outgassing torque. Another is changing activity patterns that alter which features dominate the light curve. Distinguishing a true period drift from changing light curve shape requires dense, high-quality data. Tumbling or non-principal axis rotation is another natural state. A rigid body rotates most simply about its axis of maximum moment of inertia, producing a steady spin. But impacts, close encounters, or strong outgassing torques can put a body into a tumbling state where it rotates around multiple axes. Tumbling produces light curves that are not strictly periodic or that contain multiple periods. Over time, internal friction can damp tumbling, bringing the object back to a principal axis rotation. The damping time depends on size, shape, and internal structure. For small rubble-like bodies, damping can take long times, meaning tumbling can persist. If 3I Atlas shows complex variability that resists a simple period, fit tumbling is a plausible explanation within ordinary physics. Spin stability connects to structural strength. A rapidly rotating body experiences centrifugal stress. If the stress exceeds the material's strength and gravitational cohesion, the body can shed material or break apart. For small bodies with low density and weak cohesion, there is a practical limit to how fast they can spin. In asteroid studies, there is an observed spin barrier for rubble piles, where many objects larger than a certain size do not rotate faster than a few hours because they would disrupt. Comet nuclei can be even weaker. Therefore, if a rotation period is measured to be very short, it implies either that the body is small enough that cohesion dominates, or that it has higher internal strength, or that it is a monolithic fragment rather than a loose aggregate. But in many cases, uncertainties in size and in period prevent a strong conclusion. Still, the rotation period provides a consistency check with plausible material behavior. Rotation also determines the thermal cycle on the surface. As the body spins, a point on the surface alternates between sunlight and darkness. The depth to which the temperature wave penetrates depends on thermal inertia and on the rotation period. A fast rotation produces shallow temperature variations. A slow rotation allows deeper warming. This matters for sublimation because it affects how heat reaches subsurface ice. If the surface is covered by an insulating layer, heat may not reach deeper volatiles quickly. If cracks exist, heat can penetrate and allow gas release from below. The rotation period therefore influences where and when activity occurs, and it can lead to periodic modulation of gas and dust production. Observationally, periodic changes in coma brightness or jet direction can be tied to rotation. Quietly defying expectations in the rotation region can mean that 3I Atlas shows either unusually stable behavior or unusually complex behavior. Unusually stable would mean a clean, repeating light curve with consistent amplitude and period over time, even as the object's distance and phase angle change. This could suggest a relatively inactive nucleus-dominated signal. Unusually complex would mean a light curve that changes shape with amplitude variations and irregularities that suggest activity modulation tumbling or evolving surface conditions. Both are plausible. The key is that complexity must be separated from observational artifacts. Changes in seeing can alter measured amplitude. Background stars can contaminate. Different filters can change the measured amplitude. Therefore, rotation analysis relies on careful calibration and repeated observations. The orientation of the spin axis, sometimes called the pole, is another deeper layer. The pole determines which regions receive more sunlight over the course of the approach and departure. A tilted axis can create seasonal effects, where one hemisphere is preferentially illuminated for long periods. This can concentrate activity in one region and produce an asymmetric coma. Inferring the pole requires detailed modeling of coma morphology, jet direction, changes over time, and sometimes resolved imaging. For a faint object, this may be difficult. Yet even without a pole estimate, the concept matters because it explains why activity can be localized and why non-gravitational acceleration components can include out-of-plane terms. If jets are not symmetric about the orbital plane, they can push the object slightly above or below that plane, producing a normal acceleration component. Rotation also affects dust release. If the object spins, the centrifugal force can help lift loose material, especially near the equator. If activity occurs, the combination of gas drag and centrifugal effects can make dust release more efficient in certain regions. This can influence the grain size distribution and the appearance of the coma. Over time, preferential mass loss can alter the shape and even the rotation state as mass distribution changes. These are slow effects, but they can matter over the duration of an apparition if activity is strong. In this region, the narrative remains inside the dynamic behavior of the body without yet entering the fine structure of its surface. Rotation is treated as a measurable property inferred from repeating brightness patterns and, when possible, from morphological changes in the coma. Its implications for stability and activity are framed as conditional. If the period is short and the body is large and weak, disruption becomes plausible. If the light curve is complex, tumbling or activity modulation becomes plausible. Quiet defiance of expectation can mean that rotation and activity interact in a way that resists simple modeling, requiring a patient accumulation of data and a cautious interpretation. With rotation as the governing rhythm, the next inward step is the near-surface layer, the place where sunlight first becomes heat, where volatile material first turns into gas, and where dust first detaches. This region is the boundary between the body and space. It is also where many of the observable behaviors of 3I Atlas are decided. The focus here is on near-surface physics, heating thermal gradients, crust formation cracking, and the way gas and dust move through a porous layer before escaping. These processes are not exotic. They are the ordinary physics of cold materials exposed to changing sunlight, made subtle by low gravity and by the unknown history of the object. A small icy body in space is not a clean sphere of pure ice. It is more often a mixture of ices and minerals with complex organics and with a surface altered by long exposure to radiation and micrometeoroid impacts. Over time, such exposure can produce a dark mantle. A mantle is a layer of material on the surface that differs from what lies below. In comets, a dust mantle can form when ices sublimate and leave behind non-volatile dust. This dust can settle and pack, creating an insulating layer that slows further sublimation. The thickness and permeability of this mantle determine how readily gas can escape. If gas escapes easily, activity can be sustained. If it is trapped, pressure can build below the mantle until it finds a path through a crack or weak spot. Heat penetrates a surface by conduction. The depth of penetration depends on thermal inertia and on the timescale of heating, which is set by rotation and by the change in solar distance. If 3I Atlas rotates quickly, the day-night temperature swings occur near the surface and do not reach deep. If it rotates slowly, the warming can reach deeper layers during the day and can cool more deeply at night. Over the longer time scale of its inward journey, the average temperature increases as solar distance decreases. This long-term warming can gradually move sublimation fronts inward, where a sublimation front is the boundary in the material where a volatile transitions from stable solid to active sublimation. Different volatiles have different fronts. More volatile ices can sublimate at larger distances and therefore have fronts closer to the surface earlier. Less volatile ices require more heat and may remain stable until closer to the sun. Gas flow through porous material is governed by pressure gradients and permeability. Permeability describes how easily gas can move through the pores and channels. A loosely packed layer with large pores allows easier flow. A compacted layer restricts flow. The pore structure can change over time. As sublimation occurs, pores can enlarge. As dust settles, pores can clog. As gas refreezes in colder regions, it can cement grains and seal pathways. These competing effects can lead to intermittent behavior. A patch may be quiet until a pathway opens, then active for a time, then quiet again if the pathway closes. Such intermittency is one natural way an object can appear to defy simple expectations of smooth brightening. Cracking is another key process. Thermal stress arises when different parts of the surface expand and contract at different rates due to temperature changes. Repeated cycles can produce fractures. Fractures increase permeability and expose fresh material. They can also lead to small collapses where a crust breaks and reveals volatile-rich layers beneath. If 3I Atlas has a surface that has not been previously cycled through strong heating in the solar system, it may respond differently than a typical returning comet. It may have volatiles closer to the surface, or it may have a hardened radiation-processed crust. Both possibilities affect how and when cracking leads to activity. The near surface also controls dust properties. Dust grains can be cohesive, sticking together due to electrostatic forces, van der Waals forces, or sintering, where grains fuse at contact points. In cold environments, sintering of ice can bind grains. When sublimation occurs, it can weaken bonds and loosen grains. Gas drag then lifts them. The sizes of grains lifted depend on gas flow speed and density, and on the local gravity and cohesion. Because small bodies have very low gravity, even modest gas flow can lift grains that would remain on a larger body. This can make an object dusty even at low gas production rates. The resulting coma brightness can be dominated by dust scattering, while gas remains hard to detect spectroscopically. This is another way apparent brightness can decouple from thrust and from gas signatures. A near-surface layer can also contain trapped volatiles in clathrates or in amorphous ice. Clathrates are structures where water ice forms cages that trap other molecules. Amorphous ice is a disordered form of water ice that can trap gases and release them when it transforms into crystalline ice at higher temperatures. The transition from amorphous to crystalline can release trapped gases and produce an outburst-like increase in activity. This process is considered in comet physics as a possible driver of distant activity. If 3I Atlas shows activity onset at distances where water sublimation alone is weak, such trapped gas release mechanisms become plausible within standard cometary models. Yet confirming them requires specific evidence, such as certain gas species or a particular pattern of activity. Without that evidence, they remain possibilities rather than conclusions. Quietly defying expectations at the near-surface level can mean that the object's activity seems delayed or advanced relative to typical distance-based predictions. A delayed onset could occur if a thick insulating mantle prevents heat from reaching volatile layers. An advanced onset could occur if supervolatile ices are near the surface or if amorphous ice begins crystallizing. The same near-surface physics can also produce changes in non-gravitational acceleration. If a jet turns on the thrust, can change altering residuals. If the jet is localized, its effect can depend on rotation. If multiple jets exist, they can cancel or reinforce. Therefore, the near surface is where the dynamical and photometric behaviors meet. Surface temperature itself is not uniform. The subsolar point, the point directly under the sun, is warmest. The night side is coldest. Shadows from small-scale topography can keep patches cold. If the surface is rough, some areas can be insulated. Roughness also affects how light is scattered, influencing photometry. At larger phase angles, rough surfaces can cast shadows and alter brightness in complex ways. Dust in the coma can also redeposit on the surface, changing albedo and insulating properties. This feedback can cause activity to evolve not only with distance, but with the object's own changing surface state. Another near-surface process is erosion. When gas and dust leave, they remove mass. Over time, this can sculpt the surface, widen pits, and expose deeper layers. On short timescales, erosion may be small, but even small changes can alter activity patterns if they open new vents. The surface can also undergo collapse if subsurface ice sublimates and leaves cavities. Collapse can create sudden dust release. These events, if small, can be difficult to detect, but they can contribute to variability. Again, the physics is ordinary. The surface is a delicate structure in a low-gravity environment responding to heating and mass loss. In this region, the narrative remains grounded in the boundary layer between vacuum and material. The question is not why the object behaves in a surprising way, but how a cold, porous, mixed material surface behaves when sunlight gradually strengthens. The answer is that it can behave in smooth ways or in punctuated ways, depending on mantle properties, permeability, trapped volatiles, and cracking. 3I Atlas can quietly defy expectations by expressing a particular combination of these near-surface properties, leading to activity and brightness patterns that do not follow the simplest templates. The description remains calm and measured. Heat moves inward, gas seeks pathways outward, dust follows, and the observed envelope and motion respond accordingly. With the near-surface boundary described, the next step inward is the micro-scale processes that determine how material actually transitions molecule by molecule and grain by grain from stable cold storage to escaping flow. This region focuses on the smallest physical mechanisms that still matter for what observers can measure. Sublimation, kinetics, gas diffusion through pores, dust grain lifting, scattering physics, and the chemical and electrical processes that alter grains in sunlight. These processes are not visible directly in most cases, but they set the parameters that appear in higher-level models. They are the inward end of the chain that begins with surveyed detections and ends with the behavior of matter at the smallest useful scale. Sublimation is a phase change. For a volatile solid, the rate of sublimation depends strongly on temperature. At a given temperature, there is a vapor pressure, the pressure exerted by molecules leaving the solid surface and entering the gas phase. Higher temperature increases vapor pressure sharply. In vacuum, molecules that leave the surface are not confined. They escape, and the surface continues to lose mass as long as heat is supplied. The sublimation rate is limited by how quickly heat can reach the sublimating layer and by how quickly gas can escape. If heat supply is slow, sublimation is slow. If gas escape is blocked, pressure can build and reduce net sublimation or force gas to escape through cracks. In porous materials, gas diffusion matters. Diffusion is the movement of gas molecules through the pore network. The regime can be different from diffusion in air at earth pressure because the gas density is low. In very low pressure, molecules collide less with each other and more with pore walls. This is often described as a free molecular or Knudsen regime. In such a regime, the geometry of pores and the surface roughness of grains strongly affect flow. A porous mantle can act like a filter, slowing gas and reducing its ability to carry dust. If the pore network is open, gas can escape efficiently. If it is tortuous, meaning full of twists and narrow passages, gas flow can be throttled. Over time, deposition of refrozen volatiles or fine dust can change pore size distribution and therefore change permeability. This is one microphysical pathway to changing activity, without any need for macroscopic restructuring. Dust grain lifting is set by force balance at the grain scale. Gas drag exerts a force on a grain as gas flows past it. Gravity pulls the grain down. Cohesive forces hold grains together. In the low gravity of a small body, gravitational force is tiny. Cohesion can dominate. Therefore, whether dust lifts depends mainly on whether gas drag can overcome cohesion. Cohesion depends on grain size, shape, and contact properties. Fine grains can stick strongly relative to their weight. Larger grains can have weaker cohesion relative to gas drag depending on contact areas. The result is not monotonic. Under some conditions, intermediate-size grains may be easiest to lift. If the gas flow is weak, only the finest grains may be lifted if cohesion is low, or none may lift if cohesion is high. If gas flow is stronger, larger grains can be entrained. The grain size distribution in the coma then affects the observed brightness and the scattering properties. Scattering physics at the micro scale determines how dust translates into brightness. Dust grains scatter sunlight in ways that depend on size relative to wavelength, shape, and composition. When grains are much smaller than the wavelength, scattering follows a regime often called Rayleigh, scattering with strong wavelength dependence. When grains are comparable to or larger than the wavelength, scattering becomes more complex and can be described by Mie theory for spheres as an approximation. Real comet dust grains are irregular and often aggregate, meaning they are clusters of smaller grains stuck together. Aggregates can scatter light differently than compact grains. They can also be more fragile, breaking apart as they move. The result is that the coma's brightness and color can reflect not only composition, but also grain structure. A coma that appears red may be made of grains that preferentially scatter longer wavelengths, but the cause could be composition, grain size, distribution, or both. Forward scattering is particularly important. Many dust grains scatter light strongly in the forward direction, meaning they scatter most light along the direction the light is already traveling. When the observing geometry places the observer near that forward direction, the coma can brighten significantly. This can create large changes in apparent brightness with phase angle. At the micro scale, forward scattering arises from the way electromagnetic waves interact with particles. Its strength increases for certain grain sizes and structures. Therefore, if 3I atlas shows brightness changes that seem too large for a simple distance, scaling forward, scattering by dust is a microphysical explanation that can be tested by modeling brightness versus phase angle. Gas itself can contribute to light through fluorescence. Fluorescence in cometary gases occurs when molecules absorb sunlight and re-emit at characteristic wavelengths. The efficiency depends on solar distance and on the molecule's structure. The resulting emission can be detected if the gas production rate is high enough and if the instrument is sensitive at those wavelengths. At the micro scale, this process depends on the population of molecules in specific energy states and on how quickly they are destroyed by sunlight. Photodissociation breaks molecules into fragments. Photoionization removes electrons. These processes set lifetimes. The coma composition observed at a distance is therefore not necessarily the same as the composition leaving the surface. Parent molecules can transform into daughter species. Observers often measure daughter species because they emit strongly. Interpreting those measurements requires chemical models that connect daughters to parents. This introduces uncertainty, but it remains grounded in known photochemistry. Charging of dust grains is another micro-scale effect. Sunlight can eject electrons from grain surfaces through the photoelectric effect, leaving grains positively charged. The solar wind can also deposit charges. Charged grains can interact with the solar wind's electric and magnetic fields, particularly if they are very small. This can affect the distribution of fine dust and the shape of the coma on small scales. For most grains large enough to dominate optical brightness, radiation pressure dominates. But for the smallest grains and ions, electromagnetic forces can matter. These forces can produce subtle structures or affect the evolution of the coma. They can also contribute to variability if solar wind conditions change. At the surface, micro-scale chemistry can alter material properties. Radiation can break molecular bonds and create complex organic residues. These residues can darken the surface and change its thermal properties. A darker surface absorbs more sunlight, potentially increasing heating. But a dark, porous mantle can also insulate, limiting heat penetration. The micro-scale arrangement of grains, pores, and organics therefore affects both optical behavior and thermal behavior. Over long times, cosmic rays and ultraviolet light can create a processed layer. Over short times, fresh exposure through cracking can reveal less processed material, changing reflectance and potentially changing activity. Such changes can be gradual or sudden depending on how exposure occurs. In the context of non-gravitational acceleration, microscale gas flow determines thrust. Thrust depends on mass flow rate and exhaust velocity. Exhaust velocity depends on temperature and molecular mass. If the dominant escaping gas is a lighter molecule, velocity can be higher. If the gas expands through a narrow vent, it can become more collimated, increasing net thrust. If it escapes diffusely through many pores, thrust can be more isotropic, reducing net acceleration. Thus, the microscale structure of vents and pores shapes the macroscopic acceleration. This provides a physical pathway for an object to exhibit measurable acceleration with only faint visible coma, or to show visible coma with modest acceleration. Quietly defying expectations at this microscale level means that the object's macro behavior can emerge from subtle combinations of pore structure, grain cohesion, and volatile content. A small shift in permeability can change gas escape. A small change in grain size distribution can change brightness and color. A particular phase angle can amplify forward scattering. A particular volatile mixture can shift the distance at which sublimation becomes significant. None of these require a new class of physics. They require careful attention to microphysical parameters that are rarely measured directly. This region completes the move from near-surface processes into the smallest mechanisms that underpin them. It is the inward boundary before the final synthesis of what is known and unknown. 3I Atlas remains a case where measurement meets modeling and where quiet differences from typical expectations can be explained by the micro-scale properties of cold matter responding to sunlight and vacuum. At the innermost region of this outward-to-inward path, the task is to hold together what measurement can support about 3I Atlas without turning that support into more than it is. This region remains within the smallest scale already reached, but it steps back just enough to state cleanly and calmly what is known with the strongest confidence and what remains uncertain in ways that are specific and bounded. The object's quiet defiance of expectations in this framing is not a claim of impossibility. It is a reminder that small bodies can sit at the edge of detection and at the edge of model assumptions, and that the best scientific description is one that tracks uncertainty as carefully as it tracks signal. The most stable known quantities for 3I Atlas are those anchored in repeated measurement of position and time. The object's sky track, built from many astrometric points, constrains its trajectory. From that trajectory, the orbit solution can be expressed with a perihelion distance, an inclination, an argument of perihelion, and a time of perihelion passage, each with uncertainties. From the orbit, the classification question of whether it is bound or unbound can be addressed in a barycentric frame. If the data arc is long enough and the astrometry consistent, the conclusion about an unbound path can become robust. Even then, the origin remains uncertain at the level of identifying a specific parent star system. The inbound direction and asymptotic speed can be estimated, but the backward tracing through the galaxy is limited by uncertainty growth and by gravitational perturbations over long times. Therefore, the strongest conclusion in this area is about dynamical state, not provenance. The next strongest class of statements comes from photometry, how bright the object appears over time, in which filters, and how that brightness changes with distance and geometry. From these measurements, it is possible to construct a brightness evolution that can be compared to typical comet-like or asteroid-like behavior. It is possible to search for periodic variations that suggest rotation. It is possible to place bounds on the amplitude of variation and therefore on plausible elongation, with the caveat that coma light can mask the nucleus signal. It is also possible to test for extension of the object's image and therefore for the presence of a coma using profile comparisons and aperture growth curves. If extension is repeatedly detected, then activity becomes a supported inference. If extension is not detected, activity is not excluded, but it is bounded below detection thresholds. Spectral evidence, when available, provides another layer of support. A featureless continuum suggests dominance by reflected sunlight from surface or dust. A red slope suggests wavelength-dependent scattering consistent with many small body surfaces and cometary dust. Detection of emission features supports the presence of gas and can identify specific species or at least classes of molecules. Non-detections in certain bands become upper limits on production rates. Thermal infrared detections, if present, can constrain size and albedo together. Radio line searches, if conducted, can constrain gas production for specific molecules. Across these methods, the strongest statements are those that tie directly to detections, and the most uncertain are those that require model inversion with multiple unconstrained parameters. Non-gravitational acceleration is another supported measurement when residuals demand it. If the orbit fit under gravity alone leaves systematic residuals that persist across observatories and time, and if those residuals are reduced by including non-gravitational parameters, then the existence of an additional acceleration becomes plausible. The magnitude and direction of that acceleration can be expressed with uncertainties. Interpreting it requires care, because coma-induced centroid shifts can mimic acceleration, and because the chosen distance scaling function can bias fitted values. Still, if the effect is robust, it implies that some combination of outgassing recoil and possibly radiation pressure is acting. Outgassing is the most common physical mechanism for such accelerations in small bodies. If gas is detected, outgassing becomes even more strongly supported. If gas is not detected, outgassing can still be plausible, because gas can be hard to detect at low levels while its dynamical effect can accumulate over time. From these layers of evidence, the global physical portrait remains bounded. Size cannot be uniquely determined from brightness without albedo and coma contribution. The best that can be said is that there is a plausible range narrowed if thermal data exist and widened if activity dominates brightness. Shape is constrained loosely by light curve amplitude and by the presence or absence of repeated periodicity. Mass is largely unconstrained directly, but if non-gravitational acceleration is measured, and if gas production is estimated, mass can be bounded in broad terms, and density can be discussed as consistent with porous comet-like bodies within wide ranges. Rotation period may be measurable if the light curve is sufficiently clean and well sampled, but tumbling and activity modulation can complicate period determination. Within the near surface and microphysical layers, the strongest statements are about mechanisms that are physically available. If activity begins at relatively large solar distances, then supervolatile sublimation, trapped gas release, or phase transitions in ice become plausible. If activity is delayed, then insulating mantles and low permeability become plausible. If brightness varies with phase angle strongly, then forward scattering by dust is plausible. If acceleration components suggest directional jets, then localized vents and rotation-averaged thrust become plausible. None of these require new physics. They are mechanisms established in cometary science, with outcomes that vary across objects. The remaining uncertainties can be stated with specificity. The composition of 3I Atlas at the level of particular parent molecules remains uncertain unless clear gas detections and robust spectral identifications are available. The detailed structure of its surface and the thickness of any mantle remain uncertain without resolved imaging or in situ data. The internal structure, whether it is a compact monolith, a rubble pile, or a highly porous aggregate, remains uncertain without direct mass and size measurements. The exact cause of any measured non-gravitational acceleration remains uncertain without a combined picture of gas species production rates and jet geometry. The long-term evolution of its rotation state remains uncertain unless time series data are dense and extend across the period of strongest activity. The past trajectory through interstellar space remains uncertain beyond broad inbound direction and speed. Quietly defying expectations in the most responsible sense can therefore be described as a mismatch between simple templates and the layered reality of measurement. A template might assume that brightness tracks distance smoothly, but dust scattering and phase angle can distort that. A template might assume that activity begins at certain distances, but volatile mixtures and mantles can shift onset. A template might assume that acceleration correlates with visible coma, but gas-rich and dust-poor flows can decouple the two. A template might assume stable rotation, but outgassing torques can alter spin and produce tumbling. Each of these is a known possibility. When several appear together, the object can seem to behave in a way that refuses early simplification. The most useful forward-looking statement, without previewing future zones beyond this script's inward endpoint, is that additional measurements reduce uncertainty in targeted ways. More astrometry tightens orbit and acceleration estimates. Deeper imaging and profile analysis constrain coma and nucleus contributions. Broader wavelength coverage improves composition constraints. Better time sampling refines rotation analysis. Yet even with such improvements, some uncertainties can remain because of inherent degeneracies such as size versus albedo and thrust versus mass. In those cases, the correct outcome is not forced certainty, but well-stated bounds. At this innermost region, 3I Atlas is best held as a set of measured constraints on motion, light, and possible activity mechanisms with uncertainties stated plainly. It can be interstellar with high confidence while still being chemically and structurally uncertain. It can be active with subtle signatures while remaining near the threshold of detectability. It can show small accelerations while leaving room for multiple natural drivers. The quietness is the discipline of not adding more than the data support. The defiance is the reminder that rare objects often sit where assumptions are weakest, and therefore where careful measurement and careful language matter most. Now the inward path is complete from the heliosphere down to the microphysics of escaping molecules and grains, and the description ends at the boundary of what is known and what remains open without interpretation beyond that boundary.